Hello. Hello again. So today I want us to discuss this problem. Let's read it together. A rectangle's width is 3 greater than a number. Its length is 5 reduced by that same number. What is the exact number that makes this rectangle have the maximum area? So the first, let's read that one more time. By the way, I wanna let all of you know. I'm sure you've probably heard me say it before, but whenever we're faced with a word problem, it always helps to read it at least twice. Okay, so let's read it one more time. A rectangle's width is 3 greater than a number. Its length is 5 reduced by that same number. What is the exact number that makes this rectangle have the maximum area? So the first thing we have to do is we have to translate the statement into some geometric description, some algebraic description that will enable us to use the algebraic techniques at our disposal to solve this problem. So let's do that together. So the first thing I need to do is I need to talk about, I need to give a name to the number, the mythical number that is cited in our problem. And what I'm going to do is I'm going to pick our favorite letter that has ever existed, X, to represent that mythic number, okay? I'm of course joking that it's mythic, but you know, we'll just call it our mythic number here just for fun, okay? Now, all joking aside, 3 greater than a number, okay? We can see 3 greater than a number is x plus 3, okay? This is the translation of 3 greater than a number. Now, let me convince you of this. If I ask you what is 3 greater than 1, well, you would think in your brain, aha, 4 is 3 greater than 1. And how did we get that? 1 plus 3. What is 3 greater than 5? 8. How did we do that? 5 plus 8. So I hope that I've convinced you that we translate 3 greater than a number is x plus 3, where x is the number under consideration. Now the question becomes, its length is 5 reduced by that same number. 5 reduced by that same number, okay? Aha. It must be 5 minus x. So let's write that here. So that is my translation of 5 reduced by that number. So if I asked you what is 5 reduced by 1, that's 4. 5 reduced by 3, 2. In this case, I hope I've convinced you that 5 reduced by that number is 5 minus x. Okay? So now with this behind us, we know now what its width is and what its length is. Namely, it's these numbers. So let me notate that here for our consideration. This therefore is our width, and this therefore is our length. Okay? Okay. And let me put a little semicolon here. And now we're going to have to summon a fact from geometry. We recall here that the area of a rectangle with length L and width W is L times W, where your figure looks like this. Okay? So now we're going to take that fact and we're going to take this information that we've taken from this word problem, and we're going to draw a picture of a rectangle with these as our length and width. Okay, so let me first draw my rectangle here like this. You know, I swear I told my shirt salesman that I wanted a shirt that fit me. And did you see me? I had to like kind of stretch to move this shirt to like appropriately fit me. I can't believe it. By the way, that's just a joke there. Anyway, so all joking aside here though, this is our rectangle, and we're going to put our width, let's say x plus 3 here, and we're going to put our length 5 minus x here, okay? And so now we're in a position to calculate, or at least to find an expression for the area. So I can say, okay, my area of the rectangle is going to be my length. So let's call it 5 minus x times my width, which will be x plus 3. Okay? This is my length, this is my width, right? So my area is my length times my width, so I have it. But now notice this. This is going to allow us to form, well, it's already a quadratic expression, okay? But we're going to FOIL it, okay? We're going to apply the distributive law to arrive at a form which is more suitable, okay? So 5 times x is 5x. 5 times 3 is plus 15. Negative x times x is minus x squared. Negative x times 3 is minus 3x. And then what I do is I combine the like terms. The negative x squared stands on its own. There are no like terms with an x squared. So I get minus x squared. Then I have a positive 5x and a negative 3x. So 5 minus 3 is 2. So it's going to be plus 2x plus 15. One of the things I want you to realize from here is I've essentially constructed now a formula for the area of this rectangle that if we're given the value of our number x, we can find the area. In other words, what I've just constructed here, if I want to denote it as a function, is bear with me here. I've constructed an area function that takes an input x, which is whatever number value we want to try, and it outputs the area of this rectangle, which satisfies the underlying conditions that one side is 3 greater than the number and that the other side is 5 reduced by that same number. Okay? Okay. And so now we're going to, so basically what I want you to realize is that an originally geometric problem is now translated into a question about this quadratic function. Okay? And so now we can apply the algebraic techniques to this quadratic function. Okay? And we now can begin to ask ourselves the question, okay, is there a way to maximize, so we can translate the question that was originally asked, which was, what is the exact number that makes this rectangle have the maximum area, to a question about what value of x, the number, gives us the maximum value of a. And now we know that since we're talking about a quadratic, we know that we're talking about the vertex. Now I want to make a very clear point here. Since we know that this a is negative, we know that if we were to graph this quadratic, and in fact we will, because I want to discuss a little more than that, right? But we wouldn't necessarily have to answer this question because we're going to calculate the vertex right now directly. But because the coefficient of the x squared term is negative, we know that it will be like this. And so there will actually be, in other words, it'll open down, it won't open up. And so therefore there will actually be a maximum value for the area. Okay? And there will actually be an x coordinate where that maximum value occurs, and it'll occur at the vertex. So without further ado, let's do that. And so here I have recalled for us the standard information for a quadratic f in standard form, namely a quadratic that can be written as f of x equal to ax squared plus bx plus c, the maximum, or respectively the minimum, value occurs at the vertex. The x-coordinate of the vertex, which we call x vertex, is given by x sub vertex equals negative b over 2a, where this is the b, the coefficient of the x, and the a is the coefficient of the x squared. And it is a maximum if a is negative, if the leading coefficient is negative. And we know that that's a maximum because, as I mentioned earlier, it would mean that the graph opens down. And it's a minimum otherwise. That is to say, if the a is positive. Strictly speaking, we do not consider the possibility that a is 0, because then the quadratic term would be gone and we would actually be talking about a linear equation. Okay. So now let's begin, okay? So what we have to do is we have to find the vertex of this quadratic. So let's do that together here. Okay. So first, I'm going to label, or I'm going to start calculating. My x vertex is equal to negative b over 2a. Here, we can see that my b is positive 2. So it'll be negative 2 divided by 2 times my a. What is my a? It's negative 1. Okay? Okay? Okay. Let me make a brief point here. Okay, so like if I look at this, you might say, David, are you saying that it's negative 1 because the x is 1? There's a common mistake a lot of students make, and the answer is, of course, no. What I'm saying is this. I could rewrite, if I wanted to, a of x, this area function, in terms of our mythic number x, as negative 1x squared plus 2x plus 15. In other words, what's actually happening here is that this is the way you would normally write this if you want to write all the numbers. But convention, it's a convention basically that a lot of math books use and most mathematicians use, that whenever you have 1 times x, you don't write the 1. Okay? So like this, you can just imagine it's actually this. Okay? And so that coefficient, that number in front of the x squared, is actually our a. Okay? This is our a. This number, okay, is our b. If it had been negative, it would have been negative 2. And this number is our c. Okay? Okay, now let's continue now. So now here, what's 2 times negative 1? That's negative 2, because a positive times a negative is a negative. And so I have negative 2 divided by negative 2. In other words, positive 1. Okay? So I know my x coordinate of my vertex is 1. Now, so actually, if I was actually trying to solve this problem, a rectangle's width is 3 greater than a number. Its length is 5 reduced by that same number. What is the exact number that makes this rectangle the maximum area? We would already be done. Because if you look at, because from what I just wrote behind me about a quadratic f in standard form, blah, 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 having its maximum, respectively its minimum at the vertex, and that the maximum occurs if the a is negative. We know the a is negative, as we mentioned earlier. So it's going to occur at the vertex. It didn't tell us to find the maximum area. We were finding the exact number that will make the rectangle have the maximum area, and we have found that number, x vertex. So if we were just answering the question, we'd be done. Okay? The number that'll make it have the maximum area is 1. And I want to make a brief point about this. Oh my god. So I want to make a brief point about this. So look at this width. This width would therefore be 1 plus 3, which would be 4. What would the length be? 5 minus 1. Aha. 4. The number that makes this rectangle have the maximum area is the number that forces this rectangle to be a square. So we are just witnessing in this example a particular instance that a rectangle under certain conditions has the maximum area. Okay? And let me see here. And in this part, let me see here. Stand by, please. We'll talk about what those conditions, those general conditions, are later. But for right now, I want you to notice that the constraints that we placed on this example forced it to be a square, and that we already got the maximum area. 4 times 4 is 16. But we're not going to stop there. We're going to continue with this analysis. We're going to find the vertex. We're going to graph it because I want to show you how. I want to show you a few more insights that can be gained from this example. Okay, but strictly speaking, to answer the question, we're done. The number that satisfies the relationship specified is x equals 1. Okay, but let's continue. Let me calculate the y vertex. Okay. The y coordinate of the vertex we calculate by plugging into our function. So in this case, a of 1. But what will that be? That'll be negative 1 squared plus 2 times 1 plus 15. 1 squared, we forget about the 1 for a moment. 1 squared is 1 times 1, that's 1. If I multiply it by negative, that becomes a negative 1. Okay? Plus 2 times 1 is plus 2, and then plus 15. Okay? Negative 1 plus 2, that's positive 1, plus 15. Okay? We get that that area is 16, as we got from the geometric considerations. So I can now write down my vertex. Let's look at that here. Okay, 116. 116. Like this. So now, if we want to graph this, we're going to have to find the y-intercepts. The x-intercepts, the y-intercept, and a few other details, okay? For our purposes, we're just going to find the x-intercepts, and that'll be all. Well, that'll be all for our, maybe we'll find the x-intercepts and the y-intercepts, okay? But you'll see why I'm making this determination right now, okay? Okay. So just for variety, right now, or actually, we'll just use completing the square, okay? Because so to find the x-intercepts, we set y equals 0 and we solve for x, okay? So what I'm going to do is I'm going to set this equal to 0, okay? So 0 is going to equal negative x squared plus 2x plus 15, okay? And so now what we're going to do is we want to match this with our expression over here, x squared plus 2ax plus a squared. But we see that here, there's no negative in front of the x squared, and here, unfortunately, there is. So we're going to have to factor out the negative from the whole thing. So this is going to become 0 equals negative, open bracket, x squared minus 2x minus 15. And of course, it's negative here and negative here, so that when I distribute the negative back inside, this will become plus, and this first term, the x squared term, will become negative again. Now, we recall that the question that we want to answer whenever we're doing a completing the square is that we want to match these first two terms, the x squared minus 2x, with the x squared plus 2ax over here, right? The question, in other words, is for what value of a will x squared plus 2ax equal x squared minus 2x? Okay? Now, if you were to say a equals 1, over there you would see 2 times 1 is 2, so you get x squared plus 2x, not x squared minus 2x. So it must be that a is negative 1. So let's do that over here. So I'm going to notate a equals negative 1, okay? So x minus 1 squared equals to x squared minus 2x plus, what's negative 1 squared? Negative 1 squared is negative 1 times negative 1, which is positive 1. So this becomes x squared minus 2x plus 1. So now we have figured out a way of representing x squared minus 2x. I'm going to subtract the 1 here. I'm going to subtract the 1 here. That's going to give us that x minus 1 squared minus 1 is equal to x squared minus 2x. Okay? And now, just as before, what we are going to do is we're going to replace in this expression, the x squared minus 2x, with this expression, the x minus 1 squared minus 1. So let's do that here together. So 0 is now going to equal negative, open bracket, x minus 1 squared minus 1. That's this part here. Then I'm going to bring down the minus 15 like this. And now what I'm going to do is I'm going to combine these like terms here. Okay, so I'm going to get 0 equals negative, open bracket like this, x minus 1 squared minus 16, close bracket. Now I'm going to distribute the negative inside. So it's going to be 0 equals negative x minus 1 squared plus 16. Plus 16 because this negative times this negative 16 becomes positive 16. Now from here we're going to be able to find the y-intercepts. I also want to note as a little bit of extra info, you'll notice that in no way, like when I kept the negative here, in every step of here, I haven't done anything to change this algebraically from this. All the replacements have preserved the algebraic identity because all we did was replace this by the algebraic identity that algebraic identity gave us. So what I'm saying is that as an added bonus to what we just did, I got the vertex form of my area function, which I'm going to summarize over here. Okay. So if you notice, if instead of like putting 0 here, right, if I were to put ax here, you'll see that this is totally legitimate here. By completing the square, I was just able to write this in vertex form. You can see that this does in fact have the same vertex as the vertex we got, but moreover, we're now in a position to solve the original equation by square rooting. So what we're going to do is, you see how this is minus x minus 1 squared? I'm going to add this to the other side. So I'm going to get plus x minus 1 squared plus x minus 1 squared. And I'm going to get, I'm going to put my line here. This is gone. I'm going to have x minus 1 squared equals 16. Now what I'm going to do is I'm going to square root both sides here. So I'm going to have x minus 1 equals plus minus the square root of 16. And what is that going to be? That's going to be x minus 1 equals plus minus 4. Then I'm going to add this one to the other side. Okay? And I'm going to get x equals to 1 plus minus 4. So now I can get my two roots. When I take the 1 plus 4, I'm going to get 5. So x equals to 5. And when I take 1 minus 4, I'm going to get negative 3. So x equals negative 3. Okay, so these are our two x-intercepts. Let's summarize these x-intercepts here for the purposes of referring to them when we're graphing. They're going to be 5, 0 and negative 3, 0. Okay. So now what we're going to do is we're going to find the y-intercept of this graph. So now here we're going to find the y-intercept. So what we're going to do is we're going to set the x equal to 0 and we're going to solve for y. So let's do that together. If I set the x equals 0, I get a of 0 equals what? Negative 0 squared plus 2 times 0 plus 15. 0 squared is 0 times 0, which is 0. The negative of 0 is 0. 2 times 0 is 0. So we're going to have 0 plus 15. So we're going to have y-intercept 0, 15. Okay? We already know that it opens down. We already know, and let me see here. So now we know enough to graph this, okay? So let's walk through this together, okay? And let's just summarize that equation here. Okay. So now we know that for the graph, we're going to need to reach 16 on the y, a positive 16. We're going to have the x equals 1. We're going to have to go x equals 5 on the right and negative 3 on the left. And so now we know more or less where we want to graph this x-axis. It's going to look like this. It's going to look like this. Whoops. Like this, let's see. So now let's plot this together. Okay, so like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's call it 10. 11, 12, 13, 14, 15, 16. Okay, that's 16. That's 15. Okay. 1, 2, 3. So that's negative 3 right there. 1, 2, 3, 4, 5. So that's positive 5 here. Okay. So in fact, let's put that negative 3 notation here. Put this 5 over here. Okay. We know that from here, we know that it'll touch the y-axis at 15. So I'm going to put my point there. From the vertex, we know that it goes at 1, 16. So the vertex is going to be like right here. Okay. We know that the axis of symmetry goes through x equals 1. So we know that at about x equals 2, it'll also be at height 15. Because at x equals 2, that's also one digit away from the x-axis, from the axis of symmetry. The axis of symmetry is x equals 1. So 1 unit to the left is the y-intercept, 15. So 1 unit to the right must also have height 15. We saw that our x-intercepts are negative 3 and positive 5. Okay. And so now let us draw the graph of this function. It goes like this. Okay. Man. Okay. This is the graph of my a of x. Now, the reason why I wanted to graph this for you all right now is because, number one, I want us to continue practicing these techniques of graphing quadratics, but also for a more important reason. As an algebraic function, as a quadratic function, a of x, like all quadratics, has domain negative infinity to infinity, right? Okay. And we can talk about the range. The range will go from 16 down. So the range of the quadratic will be from negative infinity all the way to 16 inclusive, okay? And it goes from negative infinity to 16 because it'll go from the bottom all the way up to the top. But the top here has a fixed finite top which occurs at the y-coordinate of the vertex for the range. But although the domain of the although the domain of the quadratic function as an algebraic function is negative infinity to infinity, from a practical perspective, we have to remember this quadratic came from a practical problem. From a practical perspective, an x value is only, let's say, reasonable to think about if it leads to a practical result that is practical in the context of the original problem. So here, for example, if I pick the value x equals negative 1, you can see that my graph is going to have some positive value. So for that, in other words, what we're saying is that that x value equals 1. When I get the y value for that x equals negative 1, that's going to correspond to a rectangle of a certain area whose area is given by this function, right? So in fact, if I were to look at negative 1 plus 3 would be 2. 5 minus negative 1 would be 5 plus 1, which would be 6. 6 times 2 would be 12. The area there would be 12. So in fact, we know that that occurs here. At negative 1, the area is 12. Okay, and if we wanted to, we could plug it in here. Let's do that together. If I take negative 1 as the x, negative 1 squared is positive 1, but the negative in front makes it negative 1 again, plus 2 times negative 1 would be negative 3 plus 15. Negative 3 plus 15 is positive 12, so that confirms what we would expect. Okay, and so if I take negative 2, you can see that it will have a certain area. If we take x equals 1, we'll have the maximum area of 16. X equals 2, we'll have the area of 15, and so on as we go along. But from this graph, these two x-intercepts, and this is why I wanted to bring these to our attention, why I wanted to calculate these more than any other parts of this graph. Because these x-intercepts correspond to the practical limits of our problem. Although the real domain of the quadratic, from an algebraic perspective, is negative infinity to infinity, from our practical perspective, our domain from practical perspective is from negative 3 to 5. Okay? Because if our number even touches negative 3, you'll see that the 5 minus negative 3 will become 5 plus 3, which will be 8, which is not bad because the length can be positive 8. But once I reach negative 3 plus 3 is 0. That causes a degenerate rectangle. It's a rectangle with basically no width. And on the other hand, if I let it reach x equals 5, we can see that the length, which is 5 minus x, would become 5 minus 5 again. So that would correspond to a width that is okay, 8, but a length that is 0. And so that's a degenerate rectangle. Okay, it's basically it has no either it'll be a rectangle with a positive width and no length, or a positive length and no width, which are both infeasible. And once we go beyond, then we'll have negative lengths. And for our purposes, for rectangle, that's not valuable. So from a practical perspective, only the x from negative 3 to 5 makes sense. And we can see that in the graph. For any x value in this region, we will get a rectangle that satisfies the conditions of our problem with a positive area. Okay, and for any x that is beyond these barriers, we will not get an area. We will not get a rectangle that is of positive area. Moreover, just to put another nice discussion here, we can see that in fact these are the values of x that make a of x positive. So in other words, we can look at it this way. So the region negative 3, 5, this interval satisfies actually a of x greater than 0. Okay? And you can see that graphically here, because all those y values within that region of x is above the x-axis, and therefore the y values are greater than 0. Okay? I hope you all have enjoyed this example, and I look forward to seeing you again soon. And thank you so much.